Welcome to the first chapter on measurements. And we start with the standard units of measurements. For many years, scientists initiated and conducted research and experimentations independently to investigate their theses and theories. And of course, this involved taking measurements of quantities, whether temperature, mass, length, time, and many others. In those days, there wasn't a standard system of units for taking these measurements. So when it came to mass, some would use pounds while others would use kilograms. If it was length, some would use centimeters while others used inches, and so on and so on. And as one can imagine, this brought a lot of problems and confusion, especially when it came to presentation of findings. So the need for a standard system was imminent. In 1960, a convention of scientists in France agreed on one international system of units to be used, the Système International des Units, French for International System of Units, abbreviated SI in all languages. In this system, there are 7 basic physical quantities: length, mass, time, electric current, thermodynamic temperature, luminous intensity, and amount of substance. According to this system, length is to be universally measured in meters. Mass would be measured in kilograms. Time would be measured in seconds. Electric current in amperes. Thermodynamic temperature in Kelvin. Luminous intensity would be measured in candela, and the amount of substance in moles. These are called the basic physical quantities because they cannot be obtained from any other physical quantities. Quantities obtained by either multiplying or dividing these basic quantities are called derived quantities. If, for instance, you divide length by time, you obtain speed. So speed is a derived quantity, and you can even tell that from its units, meters per second. That is length per unit time. Others include area, volume, density, and the list is long. In this chapter, we shall deal with length, mass, and time, and some of their derivatives. And we start with the length. Now, length is a measure of the distance between any 2 points. Breadth, width, height, radius, depth, and diameter are all lengths. The SI unit of length is meters. 1 meter is the distance between 2 marks on a standard platinum iridium bar kept at a constant temperature of 0 degrees Celsius, somewhere near Paris in France. On your screen is a table showing the multiples and submultiples of the meter. For the multiples, 10 meters is equal to 1 decameter, 100 meters is equal to 1 hectometer, 1,000 meters make a kilometer. On the submultiples, 1 meter is equivalent to 10 decimeters, 1 meter is also equivalent to 100 centimeters, 1,000 millimeters make 1 meter, and 1,000,000 micrometer make 1 meter. Length can be measured by estimation or accurately by using a measuring instrument. There are various instruments for measuring length, and the choice of the instrument is determined by the level of accuracy desired and the size of the object which is to be measured. Some instruments used to measure length are the meter rule and the tape measure. Let's look at the meter rule. Now, for day-to-day work in physics, meter rules and half-meter rules are used. They are graduated in centimeters and millimeters. Using a meter rule is pretty simple. Simply place the meter rule in contact with the object to be measured and you place the end of the object against the 0 mark on the scale. You have to position your eye perpendicularly above the scale to avoid what we call the error of parallax. So for instance, if I have to take the length of this line, if I have followed all those 3 procedures, then I can read the length of that line from my ruler. It's 6.5 centimeters. Next is a tape measure. Now there are several types of tape measures. For example, the tailor's tape measure, the carpenter's, and surveyor's tape measure. The choice of a tape measure is determined by the nature of distance to be measured. For example, to measure the length of a plot of land or the distance covered by a discus or javelin throw, a surveyor's tape measure would be the most appropriate. Now always ensure that the tape measure is taut when measuring. So how do we measure curved lengths? Now curved lengths such as roads and railway lines on a map or dimensions of some containers can be measured using a thread. The thread is placed along the required length, and the length is then found by placing the thread on a millimeter scale. Now, in these 2 methods, the length were obtained accurately. In certain cases, however, accurate determination by precise measurement is not possible. In such cases, we estimate the dimensions using a non-standard. Let's say I want to find the height of this tree. Accurate measurement would mean that I hook my tape measure at the foot of the tree and climb to the top of the last leaf and read the measurement. Of course, it's not possible. But you realize I can measure the length of the shadow of this tree. So what I do is take a ruler whose length I know, let's say 100 centimeters, and measure the length of its shadow. With these 3 values, I can get the height of the tree using the relationship height of the tree over height of the ruler is equal to the length of the tree shadow over the length of the ruler shadow. So if the ruler is 100 centimeters and its shadow is, let's say, 20 centimeters, and the tree shadow is 480 centimeters, then h, which is the height of the tree, over 100 centimeters, the height of the ruler, is equal to 480 centimeters, the length of the tree shadow, over 20 centimeters. So if I do cross multiplication, 20 times h is 20h, that should give me 100 times 480. If I divide all sides by 20, h is 2400 centimeters, which is equivalent to 24 meters. So the height of the tree is approximately 24 meters. Next is area, and this refers to the measure of surface. It is a derived quantity of length with SI units in square meters. It can also be measured in multiples and submultiples of meters squared, for example, centimeters squared and kilometers squared. Measuring area, and we start with area of regularly shaped plane figures. Now the area of regularly shaped plane surfaces such as rectangles, triangles and circles can be obtained by applying the appropriate formula. The area of a rectangle is given by length times width. So if you have a rectangle with dimension 6 meters by 4, the area is 6 times 4, which is 24 meters squared. For a triangle, area is given by a half base times height. So if I have a triangle there with base 10 and a height of 5 meters, area is a half times 10 times 5, which gives me 25 meters squared. A circle of radius 7 centimeters, area of a circle is given by pi r squared. So I shall have pi times 7 squared, which gives me 154 meters squared, and so forth and so forth. And then we look at surface area. Area of solid is called surface area, and the surface area of any solid is the sum of the area of its faces. So for example, if I need to find the surface area of this cube, if you consider the area of this front part, the length is 5 centimeters, the breadth is 5 centimeters, so the area is 25 square centimeters. Now we need to find the surface area of the entire cube, and this will be, each of the sides are equal, and there are 6 of them. So the total surface area is 6 times 25, and that gives us 125 centimeters squared. Then I have a cuboid. Considering the front face, let's find its area. It's a rectangle, length is 8 centimeters, breadth is 3 centimeters. So 8 times 3 gives me 24 square centimeters. Now notice not all sides are equal, so we work out the other faces. Consider this face. Dimensions are 5 by 3. So we have an area of 15 square centimeters. How about the top surface? The dimensions are 8 by 5, and this gives us an area of 40 square centimeters. So having these 3 different faces, we can calculate the surface area of the entire cuboid. Start with the front face, 24 square centimeters. Looking carefully, the back will be equal to this front face, so we have 2 times 24. Next, this side we have 15 square centimeters, and directly opposite will be the same. So again we have 2 times 15. And finally we have the top, which was 40 square centimeters, and it's equal to the bottom surface. So we have 2 times 40. So we add all this and we get 158. Put the units, centimeters squared. Great. And on to volume, and volume is the amount of space occupied by matter. It is also a derivative of length. The SI unit of volume is cubic meters. However, submultiples of meter cube are also used, for example centimeter cubed and millimeter cubed, because the meter cube is very large. The volume of regularly shaped solids can be determined by applying the appropriate formulas. For example, if I want to calculate the volume of this cuboid, volume is given by length times breadth times height. So for this cuboid, I'll have 8 times 5 times 3, which is going to give me 120 centimeters cubed. For the cylinder with a radius of 7 centimeters, volume is given by area of cross-section times height. The cross-section is a circle, and we saw the area of a circle is given by pi r squared. So the volume of this cylinder is pi r squared times height. So for this one we shall have pi times 7 times 7 times 10, which gives us 1540 cubic centimeters. Moving on, and we look at the volume of liquids. Now, liquids have no definite shape, but assume the shapes of the containers in which they are put. One of the methods which can be used to measure the volume of a liquid is to pour that liquid into a container of uniform cross-section. The height of the liquid is then measured, and the volume of the liquid is then obtained by applying the formula volume is equal to area of cross-section times height. If you take, for example, this cuboid whose volume we've just calculated, suppose we fill a liquid in this container. The volume of that liquid will be equal to the volume of this container, that is 120 cubic centimeters. Now, in terms of capacity, if you want to convert this volume, centimeter cubed, into milliliters or liters, we use this conversion. 1000 centimeter cubed is equivalent to 1 liter. Now, remembering that 1 liter is equal to 1000 milliliters, then it follows that 1000 centimeters cubed is equal to 1000 milliliters, and therefore 1 centimeter cube is equal to 1 milliliter. Another conversion to always remember is that 1 meter cube is equivalent to 1000 liters. A vessel with a volume of 1 meter cube will hold 1000 liters of a liquid when full. So for this cuboid, if it is filled with a liquid, what is the capacity? So it is 120 cubic centimeters. So to find the volume in liters, we divide by 1000. This is equal to 0.12 liters. 0.12 liters is equivalent to 120 mLs. In practice, however, it is convenient to make measuring vessels in cylindrical form, marked in such a way that the volumes can be read off directly. Measuring devices which are marked off like this are called measuring cylinders. Measuring cylinders are made of glass or transparent plastic and graduated in centimeter cubed or milliliters. Next, we look at measuring the volume of an irregularly shaped solid. Now, volumes of irregular solids are measured using the displacement method. The method works with solids that are not soluble in water, do not absorb water, do not react with water, and will sink in the water. One of the methods of measuring such solids is using a Eureka can. Now, a Eureka or displacement can is a container with a spout from the side. It is used to measure volumes by displacement method. We first fill the Eureka can with water until it flows out of the spout. And once the flow has stopped, we place a measuring cylinder under the spout. Then you tie the solid whose volume you want to determine with a thread and lower it gently into the can until it is completely submerged. Now, the volume of the water collected in the measuring cylinder is the volume of the object. Another way of measuring the volume of irregular solids is using a measuring cylinder. Now, we partly fill a measuring cylinder with water and note the volume. And then the stone is tied and lowered gently into the cylinder until it is wholly submerged. And we make sure that there are no air bubbles that surround the solid. We record the new volume, and the difference in volumes of the liquid in the measuring cylinder is the volume of the solid being moved. Next is mass, and mass mass is the quantity of matter in an object. Matter is anything that occupies space, so it also has volume. The mass of an object depends on its size and the number of particles it contains. The SI unit of mass is kilogram, and a kilogram is the mass of a piece of metal, platinum iridium, kept near Paris in France. Some of the commonly used submultiples and multiples of kilograms are shown on your screen. 1,000 grams make 1 kilogram. 1,000 kilograms is equivalent to a ton. 1,000,000 milligrams will make a kilogram. The mass of an object is the same everywhere because the number of particles in that object remains constant. An object will have the same mass on Earth as on the Moon. There are two common types of balances for measuring mass, which are either electrical or mechanical. Now on your screen is a top pan balance, which is electrical in nature. The object whose mass is to be measured is placed on the pan. The mass of the object is read on the display. This type of balance is very accurate. Again, we have a simple form of a beam balance, which is of mechanical type. The object whose mass is to be measured is balanced against a non-standard mass on an equal arm lever as shown on the screen. The beam balances when the mass of the object is equal to the non-standard mass. You've seen this kind of balances in butcheries and in shops. These type of balances are, however, extremely limited because you can only measure the mass which is equivalent to the standards that one has. There are also instruments which are designed to measure huge masses, for example that of trucks on way bridges and in factories. Next is density, and density is mass per unit volume of a substance. Its symbol is rho and the SI unit is kilogram per cubic meter. Another commonly used unit is gram per centimeter cubed. From the definition, the density of a substance is given by density is equal to mass over volume, rho is m over v. For example, if you have a density of 1 gram per centimeter cube and you want to convert into SI units, you first convert the gram into kilograms and then the centimeter cubed into meter cubed. And then you divide the mass and the volume and you shall find 1 gram per centimeter cube is equal to 1,000 kilograms per centimeter cube. Let's take an example. Suppose 25 centimeters cubed of ivory is found to be 0.045 kilograms. Calculate the density of the ivory in SI units. Solution. For me, I would prefer to first convert the kilograms into grams. So I multiply by 1,000 and I get 45 grams. So density is mass over volume. 45 grams divided by 25 centimeters cube, I get 1.8 gram per centimeter cube. To convert into kilograms per meter cube, I simply multiply by 1,000 and I get 1,800 kilograms per meter cube. Another example, suppose the tank shown on your screen is filled with water. Calculate the mass of water in the tank. And we are given the density of water is 1,000 kilograms per meter cubed. Now the volume of the tank will be given by length times width times height, that is 12.5 times 10 times 2, which gives us 250. If density is mass over volume, then mass is density times volume. So we have density 1000 kilograms per meter cubed times volume 250, and we get that to be 250,000 kilograms. This is equivalent to 250 tons. What about density of mixtures? Now, a mixture is obtained by putting together two or more substances such that they do not react with one another. The density of the mixture lies between the densities of its constituent substances and depend on their proportions. It is assumed that the volume of the mixture is equal to the sum of the volumes of the individual constituents. Density of the mixture is equal to mass of the mixture over the volume of the mixture. Let's take an example. Bronze is made by mixing copper and tin in the ratio 4:1. If the density of copper is 8,900 kilograms per meter cubed and that of tin is 7,000 kilograms per meter cubed, calculate the density of 100 kilograms of bronze. Now recall that density of the mixture is equal to mass of the mixture times volume of the mixture. The mixture is bronze, so we have its mass already. So what we need to find is the volume of the mixture. Now to get the volume of the mixture, we need the volume of individual constituents, that is copper and tin. So mass of the copper from the ratio 4:1 will be given by 4/5 times 100, which gives us 80 kilograms. Mass of tin, again from that ratio, is 1/5 times 100, which gives us 20 kilograms. So that will now allow us to calculate the volumes. Volume of copper is equal to mass of copper over density of copper. That is 80 over 8,900. That gives us 0.00899 meter cubed. Volume of tin is equal to mass of tin over density of tin. Mass of tin is 20 kilograms. Density is 7,000 kilograms per meter cubed. If you divide that, we get 0.00286 meter cubed. Volume of bronze, which is the mixture, is equal to volume of copper plus volume of tin. So that gives us 0.01185 meter cubed. Density of bronze is mass of bronze over volume of bronze. The mass is 10 kilograms. The volume is what we just calculated, 0.01185. If we divide that, we get 8,439 kilograms per meter cubed. That is the density of the bronze.
You can make a bigger difference in the world. You can make a positive change in your career. You can make a greater contribution to the greater good. And you can start today by earning your degree online at Walden University, where advanced degrees advance the quality of life.